Welcome to the chapter on semiconductors. Semiconductors are the backbone of modern electronics, including devices like diodes, transistors, and integrated circuits. In this chapter, we will explore the fundamental concepts of semiconductors, their components, and their applications. Semiconductors, like silicon and germanium, have electrical conductivity that sits between conductors like copper and insulators like glass. This special property makes them ideal for controlling electrical current in electronic devices. By adding impurities, a process called doping, we create two types of semiconductors: P-type, which has positive charge carriers called holes, and N-type, which has extra electrons. When we combine P-type and N-type semiconductors, we get a PN junction, a critical building block for devices like diodes and transistors. Semiconductors are materials that have electrical conductivity between that of a conductor and an insulator. Their ability to conduct electricity depends on the presence of free electrons or holes, which are places where an electron is absent. This property makes semiconductors vital in modern electronics, including transistors, diodes, and solar cells. Silicon and germanium are common examples of semiconductor materials. To alter the electrical properties of semiconductors, impurities are introduced in a process called doping. This creates two types of semiconductors, P-type and N-type. In P-type semiconductors, impurities introduce holes, which act as positive charge carriers. In N-type semiconductors, impurities introduce free electrons, which serve as negative charge carriers. A PN junction is formed by joining P-type and N-type semiconductors. The P-type semiconductor, rich in holes, and the N-type semiconductor, rich in free electrons, interact at the junction. Electrons from the N-type region diffuse into the P-type region and recombine with holes, leading to the formation of a depletion region. This depletion region acts as a barrier, preventing further movement of charge carriers, and is crucial for the functioning of semiconductor devices like diodes. P-type semiconductors are doped with elements that have fewer electrons than silicon, creating holes. For example, when silicon is doped with boron, the boron atoms create holes by accepting electrons from neighboring silicon atoms. On the other hand, N-type semiconductors are doped with elements that have more electrons than silicon, providing extra electrons. For instance, when silicon is doped with phosphorus, the phosphorus atoms contribute extra electrons, enhancing the material's conductivity. A diode is a semiconductor device that allows current to flow in one direction only. It is formed by a single PN junction and has two terminals, anode and cathode. The structure of a diode consists of an anode, which is connected to the P-type semiconductor, and a cathode, which is connected to the N-type semiconductor. When a positive voltage is applied to the anode relative to the cathode, known as forward bias, the depletion region narrows, allowing current to flow. Conversely, when a negative voltage is applied, known as reverse bias, the depletion region widens, preventing current flow. The current through a diode in forward bias can be described by the Shockley diode equation. The formula is I equals I sub s times the exponential of V sub d divided by NV sub t minus 1. Here, I is the diode current, I sub s is the saturation current, V sub d is the voltage across the diode, N is the ideality factor, typically between 1 and 2, and V sub t is the thermal voltage, which is Kt divided by Q. In this context, K is the Boltzmann constant, which relates the average kinetic energy of particles in a gas with the temperature. T is the absolute temperature in Kelvin, representing the thermal energy available. Finally, Q is the elementary charge, the charge of a single electron, which influences how the thermal energy translates to voltage in the diode. An LED, or light-emitting diode, is a special type of diode that emits light when current flows through it. The color of the light depends on the materials used in the semiconductor. When an LED is forward biased, electrons recombine with holes in the P-type region, releasing energy in the form of photons, or light. The wavelength, or color, of the emitted light is determined by the energy gap of the semiconductor materials. Transistors are semiconductor devices used to amplify or switch electronic signals. There are two main types of transistors: bipolar junction transistors, or BJTs, and field effect transistors, or FETs. A bipolar junction transistor, or BJT, consists of three layers of semiconductor material forming two PN junctions. There are two types of BJTs, NPN and PNP. In an NPN transistor, a small current input to the base allows a larger current to flow from the collector to the emitter. In a PNP transistor, a small current flowing out of the base allows a larger current to flow from the emitter to the collector. The current gain of a BJT is given by the formula beta equals I sub C divided by I sub B. Here, beta is the current gain, I sub C is the collector current, and I sub B is the base current. Field effect transistors, or FETs, control the flow of current by applying a voltage to the gate terminal, which creates an electric field that modulates the conductivity of a channel. There are two types of FETs: junction field effect transistors, or JFETs, and metal oxide semiconductor field effect transistors, or MOSFETs. The current through a MOSFET in the linear region is given by the formula I sub D equals mu sub n C sub aux times W divided by L times the quantity V sub GS minus V sub G8 times V sub DS. Here, I sub D is the drain current, mu sub n is the electron mobility, C sub aux is the oxide capacitance per unit area, W is the channel width, L is the channel length, V sub GS is the gate source voltage, V sub ith is the threshold voltage, and V sub DS is the drain source voltage. Understanding semiconductors and their components is crucial for any electrical engineering student. Diodes and transistors form the basis of most electronic devices, and mastering their principles is essential for progressing in the field of electronics.